There's block number 1, and we will use, how about pink for the other one? There is block number 2. And we'll say that this one has mass M1, and this one has mass M2. And now let's pull on the top block. Okay. And we're going to pull on it such that we want to find the maximum F pull that the blocks still don't move. How hard can you pull on that top block such that none of the blocks move? Okay, to do this, we're going to probably need a little bit more information than just the masses. What other information are we going to need? What do you guys think? What's holding those blocks in place if I try to pull on them? Static friction, exactly what we just talked about, right? Static friction is holding them in place, and so we're going to need to know the coefficients of static friction. And this is where it gets a little bit cumbersome because we have two surfaces to worry about. Block M1 is sitting on block M2, and so there is some coefficient of static friction between block 1 and 2. This is what I mean by all these subscripts. Okay? So we don't know exactly what that is, but that would be some number. And then we can just make something up. How about 0.6? And then there is another coefficient of friction between M2 and the table. So this would be static friction between block 2 and the table, and maybe that is 0.5. So these you would be given in the problem. Okay. And if you had numbers for there, you would also be given the masses and so forth. So what do we do now? We've got a picture. We need to go to the free body diagram. And when we go to the free body diagram, we have to treat each one independently. So let's see what the free body diagram is going to look like for M1. So M1 becomes a dot. What are the forces that are acting on M1? Just shout them out. What do you guys think? What's the first one we always draw? Yeah, gravity. M1G, gravity going down on box M1. What else? Normal force, and this is where we need to be specific about which normal force we're talking about. Normal force on block 1 due to block 2. Okay? Normal force on 1 due to 2. What else? Well, we said we're going to pull it, right? F pull. So that's to the right. Static friction, which way? Yeah, if it's not moving, there's got to be something that's going to balance out F pull, and that would be static friction going this way. F sub S, but we need to put some more subscripts on it because this is static frictional force on block 1 due to block 2. Okay? Let's take a look at M2. M2, of course, has gravity. What else is acting on M2? Okay. M1 is acting on M2. M1 is sitting on M2. So what is the force that I need to put on this picture? What should I label it? Okay. Not mg yet, but normal force of 2 onto 1. N12 was up, N21 is down. This is block 1 pushing on block 2. It might be that we see that that is in fact equal to M1 times G, but let's keep it like this for now to keep it general. Anything else? There's got to be something else if the whole thing's at rest, right? What's that? N2T. So there must be some normal force on 2 due to the table, right? The table is holding up block number 2. What else? It's not moving, so this could be it. But we know that there's somebody trying to pull on this thing, and so there's got to be something else holding this whole thing in place, which is static friction on 2 due to the table. And then there is some force to the right to balance that out, which is what? It's F sub S 2, 1, the static friction on 2 due to block 1. Okay, so this is what I mean when I say these things get kind of complicated quickly, right? Because look at that simple picture and look at this mess that we have over here, right? It's a nightmare. It's not a nightmare, but it's a bad dream. So what are the action-reaction pairs that we have just identified? N12 goes with N21. Okay, block 1 is pushing on 2, but block 2 is pushing on block 1. Is there another action-reaction pair that we've identified? Yes, it is FS12 and FS21. The frictional force here is exactly equal and opposite to the frictional force there. Okay? And we know that those magnitudes are equal. Magnitude of N12 equals the magnitude of N21. Magnitude of FS12 equals the magnitude of FS21. These are the action-reaction pairs that we're talking about in this chapter. Okay? So now that we have this free body diagram set up, how are we going to deal with this problem? How could we possibly figure out what is the maximum pull that we could have and this thing still doesn't move? Well, we need to do some math, right? We need to write down Newton's second law, and then we have to do some math. So let's do that. We've got number 1, sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. F pull minus Fs12 is equal to 0. The whole thing's at rest. Okay. The vertical components, not too bad. Sum of the forces in the y direction equals the mass times the acceleration in the y direction. We get N12 minus M1g. That also equals 0. What about for the second one? For the second one, we have sum of the forces in the x direction. What do we have? We have Fs21 minus Fs2t. That equals 0. And then we have the vertical forces, N2t minus M2g minus N21. All of that equals 0. And this was, of course, the vertical equation. That's writing down Newton's second law. And now if we're going to figure out the maximum F pull, we need to do one more thing. We need to realize that static friction, for instance, Fs12 is less than or equal to mu S12 times the normal force on 1 due to 2. And Fs2t is less than or equal to mu S2t times the normal force on 2 due to the table. So how do you figure out the max pull? You set these to the maximum. Okay? You set them to equal, and then you figure out how to solve for F pull. Okay? Questions about this approach? You can see why Newton just said, for every action there's an equal and opposite reaction, because otherwise it gets really complicated very quickly.